All right, hello. So this is video number 2 of section 6.2. And if you couldn't already tell, this is going to be an extremely fun lecture because I'm wearing my fun hat. So the problem I want to talk about in this video is the problem of, you could say, approximating one vector using another vector. And so I kind of put approximate in quotes because it's a little bit of a loose way of describing what's going on. So what we actually want to do, and we can picture this best in the two-dimensional plane, but the concepts we're going to talk about can be expanded to vectors of any length, really. We want to find a vector that is the scalar multiple of u, or a scalar multiple of u, I should say, that is closest in distance to the vector y. Meaning, I want to find, so first off, notice that all of the scalar multiples of u lie on this line L that can be sort of extended from u, and I tried my best to draw it parallel to u. But if you imagine just sort of drawing the infinite line going off in the direction defined by u, all of the scalar multiples of the vectors of u, all of the scalar multiples of u lie on this line, right? And so you can imagine basically either expanding u in this direction or reversing direction if we multiply by the right sort of negative constant. And so what we want is the vector that lies on this line that defines the point closest to this point defined by the vector y. And so it turns out, somewhat logically, the vector that does this is the vector y hat, which we will define in a minute, such that this vector, which we will call for now z, forms a right angle with the line L defined by u. And so if you can imagine, basically, this line forming a right angle means we have the straightest shot from y hat to y. Well, we know that in this case, z is going to be orthogonal to u, right? So we actually do know a lot sort of about what is going on here. And so what we can do, we know that z is orthogonal to u, right? Because it forms a 90-degree angle with the line defined by u, or z is orthogonal to y hat, whichever vector you prefer. We also know that y hat is a scalar multiple of u. So what we can do is we can define y hat and z in terms of u and y. And so the first thing to notice here in solving this problem is that y is going to equal y hat plus z. And so here, notice y hat is a scalar multiple of u. Z is orthogonal to u. And we won't prove this now, but we pick z because the length of, well, so notice then in this case then that z is equal to y minus y hat, if we've chosen this correct vector z correctly, where z has minimum distance. And so in this case, we choose y hat so that the length of z, which is equal to the distance from y to y hat, is minimum. So kind of reiterating what we've got so far, we've shown that, okay, if we want to approximate y using u, or find this sort of scalar multiple of u which is closest to y, we want to find the vector that lies on the line defined by u, such that the vector, in a sense, connecting y hat and y is orthogonal to u. z. The reason being is if this vector is orthogonal to u, then the length of z, which is also the length of y minus y hat, is minimized. And so sort of our goal here is to find the vector y hat, which is a scalar multiple of u, such that the value of this is minimized. So how are we going to do that? Well, remember that we know that z is equal to y minus y hat, and that y hat is actually a scalar multiple of u, which we'll call alpha times u. Right, so y hat is actually equal to alpha times u, where alpha is just some scalar that we've chosen. And so what we want, right, is we want to choose this scalar alpha so that the dot product of u and z is equal to 0. So we know that dot product of u and z should be equal to 0 because z should be orthogonal to u. Therefore, 0 should equal u dot product y minus alpha times u. And so we can use this equation here to solve for alpha. And notice solving for alpha in terms of y and u will give us y hat, which will eventually give us z. So now, solving for alpha, well, what we can do is distribute this dot product, subtract this over and divide. We get that alpha is equal to u dot y over u dot u. Well, that means, and so notice in particular, alpha itself is just a scalar, right? The dot product of two vectors is itself a scalar. And so this is some scalar over some scalar. And so that means y hat, remember, which is the scalar multiple of u closest in distance to y, is the vector u dot y over u dot u. And so this is a scalar times the vector u. And so this is called the orthogonal projection of y onto u. And we've got some more notation for this sort of thing in a bit, but I want to talk a little more about what we just found. So orthogonal projection of y onto u. Another way you can think of sort of this definition is we are kind of like taking y and sort of folding it down onto u, and we want to minimize this distance that does this, right? And so what we're doing is we're not calculating this vector per se, which is the vector which actually defines the distance. We're calculating the vector y hat, which is a scalar multiple of u, which is the vector we're sort of going to collapse y down onto. Right? So this is the vector that when we collapse y down onto this line, we're collapsing y onto y hat, which is the orthogonal projection of y onto u. And so we've then actually already defined how we can define z after finding y hat, right? So if we've solved for y hat, which notice here, to solve for y hat, we've shown we only need u and y. And so then once we've solved for y hat, we can solve for z, where z is just equal to y minus y hat. And so then the minimum distance from y to a scalar multiple of u is just given by the distance from y to y hat. And so we've got a little more notation that we sometimes use when describing these vectors. So we'll often say that y hat is equal to the projection of, and I have to make sure the order here is right because this can sometimes be a little confusing, the projection of y onto u. So this notation, and sometimes if we've defined this line L, I don't love this, but your book will sometimes do this. We'll define this as the projection of y onto the line L. So be very careful with this notation. This vector y hat is the projection of y onto u. So if you're reading this, you have to read the superscript and then the subscript, because the order here definitely matters, right? The projection of y onto u is very different from the projection of u onto y. And so if we calculate this vector, which again, just given the original vectors y and u, is fairly straightforward to calculate, we can then calculate the minimum distance from y to the line defined by u by calculating this vector z, and then finding the length of z, which it turns out is just the length of y minus y hat. So solving the problem of approximating y with u, it turns out isn't that hard. We just have to use this, the orthogonal projection of y onto u. So I actually just want to wrap this video up with one example where we do this. And so note that this idea, and this definition of vectors, before we move on, this works in any dimension Rn. It's just beyond maybe 3 dimensions, and I don't even trust myself to draw this good in 3 dimensions. It gets hard to draw the picture, right? So in 2 dimensions, this picture of sort of being at a right angle, minimizing this distance or minimizing the length of z makes a lot of sense. But once you get into higher dimensions, it becomes impossible to draw. But still, basically in higher dimensions, all you're doing is you're doing the same thing, right? You're calculating the scalar multiple of u. Z is equal to the difference of these 2 vectors, and in higher dimensions, basically the length of z is still the length between y and y hat. So, sort of these properties of orthogonality, minimizing distance in this way, hold in all dimensions Rn. And so we will occasionally do this with vectors in 3 or 4 dimensions as well. But I just want to wrap up with an example in 2 dimensions, 2-dimensional space, R2. I'm going to leave the picture up just so we can continue to sort of have a reference of what's going on here. You'll just have to imagine, I think the vectors are going to be clearly not in the first quadrant here, but you'll just have to imagine that they are. So we've got a few things we want to do with this example. We're going to let y equal the vector 2, 3, and u equal the vector 4, negative 7. So we want to compute the projection of y onto u. Then we want to write y as the sum of 2 orthogonal vectors. And this is basically just describing exactly what we did before. Your book kind of describes it in this way sometimes. One in span u, and so this vector is going to be y hat, and one orthogonal to u, and so that vector orthogonal to u is going to be z. And then finally, we want to calculate the distance from y to the line defined by u. and that will just be the length of the vector z we eventually calculate. So in this picture, the projection of y onto u is the vector y hat. Y as the sum of two orthogonal vectors will be the vector y hat plus z. And so notice specifically y hat plus z is always equal to y. And then the distance from y to the line defined by u will be the length of z. So first things first, let us calculate the projection of y onto u. So remember, this is equal to y dot u over u dot u times the vector u. And so this can sometimes be a little involved, especially when you start to get into higher dimensions. So this should be 2 times 4 plus 3 times negative 7. All over u dot u, which should be 4 squared plus negative 7 squared, times the vector u, which is 4, negative 7. So a few things in this calculation. Notice again that this fraction part here of the fraction of the dot products is just a scalar, right? These are going to eventually crunch down a bit and just turn into a scalar. But the projection of y onto u, again, y hat in the picture, is a vector, right? So this last u here is what's going to make this a vector. And specifically, because this is a scalar, this is in fact just a scalar multiple of u. So this is equal to 8 minus 21 over 16 plus 49 times the vector u. 8 minus 21 is negative 13. Yeah. And 16 plus 49 is 65 times 4, negative 7. So this is equal to negative 1/5 times the vector 4, negative 7. And so this is the vector negative 4/5, 7/5. And this is equal to the projection of y onto u. And make those a little more distinct there. U, y, which, remember, in this picture is the vector y hat. So this is projection of y onto u. So we want to write y as the sum of two orthogonal vectors. In span of u, that's y hat and z. So now remember, z is equal to y minus y hat. So the vector z should be 2, 3 minus negative 4/5, 7/5, which is equal to 14 over 5. This is 15 over 5, 8 over 5. And so this means that y is equal to negative 4 over 5, 7 over 5, plus 14 over 5, 8 over 5. And so this would be the second part of our answer. And so notice in particular, this vector is a scalar multiple of u, and this vector here is orthogonal to u. And so we're almost done. We just want to calculate the distance from y to the line defined by u. And remember, all that this distance is just the length of this vector z. So distance is equal to the norm of y minus y hat is equal to the norm of z, which is equal to the square root 14 over 5 squared plus 8 over 5 squared, which is equal to 14 squared, which is, gonna have to quickly figure that out, 256, 196. 196 over 25 plus 64 over 25, which is equal to 260 over 25, which is the square root of 260 over 5. So, projection of y onto u is this vector, negative 4/5, 7/5. This is the vector that is a scalar multiple of u that is closest in distance to y. This vector z is the red vector here, whose length basically defines the smallest length from y hat, or from this line L to y. Specifically, y is equal to y hat plus z. And then the length of z actually gives the shortest distance from y to the line defined by u. And we can do it all using this sort of idea of orthogonal vectors and orthogonal projections.